All right. Well, welcome back, everybody, to the View Dependent podcast, where we speak to researchers and creative entrepreneurs creating in the world of very lifelike 3D through different radiance field representations, such as Gaussian splatting. And today we have a very exciting guest to have on the show. His name is Isaac Deutsch from the NVIDIA research team, and we're super, super excited to have you on today.
Yeah, thank you so much. I'm super excited to be here, and thank you for inviting me as well.
I'm also super excited to have you here because some of your inventions are also powering Lichtfeld Studio, which is very exciting, and many people enjoy it. And I think they are also curious to know more about this technique from the original. So very glad to have you here.
Yes,
of course.
So today we're going to be talking about one of your methods called PPISP, otherwise known as Physically-Plausible Image Signal Processing for Radiance Fields. And it's a very impactful paper and one that was super quickly adopted through this entire community. So before we get to that, though, I'd love for you to actually introduce yourself and tell us a little bit about your role at NVIDIA.
Yeah, sure. I'm a research scientist at NVIDIA. Before I joined NVIDIA, I studied robotics and control at ETH Zurich. That was already more than 8 years ago, and so I joined NVIDIA. And recently, I've been working mostly on research and development on the NuRec project. And as part of that work, this also spawned this PPISP research project as well.
Was something like 3D reconstruction something you did before joining NVIDIA? So was it already part of your robotics degree?
Yeah, you could say that. As for when I first encountered that, I have a little story time. So when I was a kid, there used to be these magazines, with CD-ROMs contained in them. And often I would, and I was lucky enough that my dad would let me play with the shareware and the software demos on there. And I remember as one of these CDs, there was actually one with a kind of 3D reconstruction software back then. So basically, you could print a sheet of paper with these markers on it, and then it would use shape from silhouette to carve out your object. And I remember being really amazed by that. That's the first time I came in contact. And then later during my studies, I came in contact with that again. So I remember I was looking for a bachelor thesis for a supervisor, and I was asking different professors. And one of them was like, "Oh, I'm so sorry, Isaac, I cannot supervise you at ETH because I'm going to Hong Kong. But if you want, you can join me." And I was like, "Oh, that's so cool. I want to go there anyway." And so no matter what it is, I'm going to be doing. And there I worked on SLAM, which is simultaneous localization mapping, which is a really common problem in robotics and well researched. And the mapping part of that is also kind of 2D or 3D reconstruction as well.
Nice. And so then, do you remember when you first came across any of the radiance field representations? Was it through NeRF or Gaussian splatting or a different one? Or what kind of started the more modern research, I guess, for your current line of research?
Yeah. Back then, we were working on a RGBD SLAM. So that's a SLAM from color and depth information. And we were also working with these kind of point-based representations. And then we have on the internal Slack chat, we have some channels that are specifically for new papers, etc. And I remember seeing the original NeRF paper and some of the results, this kind of circular camera motion for the novel view. And I remember being very amazed by the quality. That's when I first saw the NeRFs in action, so to speak, with the very first original publication.
And then it was kind of just from there. Now it's really focusing on creating lifelike 3D from 2D images.
Not directly. So we, I think back around in 2021, we had a really brilliant intern with whom we worked a little bit on NeRFs. NeRFs back then, it was like you train for 20 hours and then you start to see something, right? And we were looking at some kind of depth supervision. And I think for me, when the point where I got really pulled in was a bit later, when Thomas Müller, Alex Evans et al., they were working on instant NGP. And back then, we were still working on our RGBD SLAM as well. And we had the idea of combining the two. So we were using the camera tracking from our SLAM because it was running in real time, and this NeRF reconstruction with instant NGP was also almost, you could say, real time. And so this resulted in this work in this demo at it's called the real-time live demo at SIGGRAPH 2022. That's what really spawned it. And Nico, one of the co-authors of the PPISP paper as well, back then was also already working on rendering of NeRFs in Omniverse. And if we could have a almost real-time reconstruction of NeRFs as well as a really fast rendering in Omniverse, that could be really interesting for like different robotics applications as well.
And then you came how about in contact with 3D Gaussian splatting? Was it just like the natural follow-up work you were starting to work with?
Yes, I remember actually Thomas himself posting, "Oh, this is going to be the next state-of-the-art approach." So he really saw the potential early in the 3D Gaussian splatting. Yeah.
And so since then, there's been so much excitement and research work building on top of both like NeRF and Gaussian splatting in the last few years. And some of the really impactful papers, at least for me, there was another one called Bilateral Guided Radiance Field Processing that really was able to recover a lot more and disentangle a lot more exposure information. And then earlier this year, you published PPISP, which kind of takes that to a whole other level. And now we're able to recover even more information about a given capture across different, exposure or camera parameters. And so I was wondering if you could talk a little bit about PPISP now and moving into this world about really starting to bring back information.
Yes, sure. So yeah, we did also see bilateral grids, and then we had an implementation internally that I worked on because the topic itself was interesting to me. And we started noticing a few shortcomings or like things that are difficult to work around with in bilateral grids. And so PPISP really started as a kind of a idea to try to improve on some of these shortcomings that we had with bilateral grids. And then at some point later, we decided to, maybe we can actually try to publish this as well. So that's how the project came to be. We have a few different submodules in PPISP. And actually, we realized later that this closely follows another published approach called ADOP, approximately differentiable 1 point or 1 pixel rendering. But that when we tried that, it also had a few issues. So in PPISP, we have the 4 basic modules, which are the exposure correction, the color correction, the vignetting correction, and then the camera response function, which is a kind of tone mapping. And all of these, we like to call them physically plausible because they're modeled after real optical effects or also this kind of ISP processing that is commonly found in many cameras as well.
Maybe we can start from a little bit higher abstract level. So if you take a 3D capture, you're trying to capture a radiance field, no matter which method you use. What are the problems? So let's say you capture like 300 images, and now is this like a faithful representation of the object you want to capture, or what are the problems? So the guy who is capturing, which problems does he face, and how does it relate to the problem you are trying to solve?
I dove right in, but you're right. So the issue is that when you take a photo, right, with a camera, it's a representation. And basically, with radiance fields, they follow this volumetric rendering, which is differentiable, which is the basic formulation. And any kind of effect that you have in your camera, which is besides the pure measurement of the, let's call it the sensor irradiance, so the light that reaches the camera sensor, it's not going to be modeled by this basic formulation. So I would say actually a camera, since it has usually this Bayer pattern, etc., it more closely matches the human vision system. So we have a certain like spectral response to certain light frequencies. So maybe we should call it like neural luminance fields instead. No, but what I'm saying is between the light reaching the sensor and the image, there's a certain processing, right? And if you don't account for that or model that in some way, then the 3D reconstruction will have to explain somehow where these effects come from. And usually that results in these kind of floaters or like spotty surfaces, or, with NeRFs, it used to be more like these cloudy artifacts. And basically, with PPISP and other similar such approaches, one of the ideas is that we can explain them away. And of course, with PPISP, we also try to show that we can also transfer that to novel views as well to improve the faithfulness of the novel view that we render.
So this basically means if you're having multiple captures or multiple images, even they look at the same object and you take them side by side, they may look different, right? So
yes,
they explain the object, but they may have like a color shift or white balance shift or something like this, right?
Yeah, there's different sources for this, right? So you already said the most important ones, which is if you move the camera around and then set to automatic settings, for example, and suddenly the sun enters the frame, the camera is going to dial back the exposure, which makes everything darker. And then suddenly the same spot on the surface of the object you're trying to reconstruct may appear differently across your images. And this will result also in a bad reconstruction in some cases, as you said. And besides that, you can also have some optical defects, such as the corner darkening. So this is really common. So with PPISP, we try to model like the most common sources for these artifacts.
Is there something like, I mean, if you like have this method PPISP, is this something that tries to improve the reconstruction based on the correction of the images, or is it something that just tries to improve the camera model? Can you tell something about that?
Do you mean in comparison to like previous work, or improve in what way?
No, I mean in general, because now you're trying to equalize like all the images that they look more or less like equally, right? So let's say they don't look equal. What happens then? Is there something like a side effect that can happen?
Oh, now I understand. Yeah, basically, the idea is that of a underlying consistent reconstruction. So we have the geometry, as you said, it's usually fixed. Like it's some object in space that's not changing while you're capturing it, but the way you're capturing it, this may change. And so what happens is we have this underlying consistent reconstruction, and your appearance model in this case, for example, PPISP, will then go from this consistent rendering, which is in a more like raw or basic state, and then reconstruct the look of each image that you've captured as well. And by that mechanism, it can explain away the differences that you have in your captures.
And so you have these like 4 different modules as part of PPISP, and I am like curious about how you both like arrived at the specific ordering and those grouping of parameters. Like, were there other components that perhaps you also tried and either dropped or decided to not include for the time being?
Yes. Okay, that's several questions. So first of all, about the ordering. So we try to follow some more foundational work, like there's a Debevec and Malik, which is this older work, and they say basically when the light goes through the optics and arrives at the sensor and is then processed, there's a few steps of linear operations, also on color information, which is in a linear color space. And then at the end, you have a non-linear mapping from the linear color space to the display color space, usually something like sRGB for our displays, for example. So we try to follow that more or less. And then for extra components, yes, I explained the 4 we have briefly, but we also tried to have an extra component called responsivity, which was supposed to model how different cameras react to light in terms of their overall reactiveness to light. So translating from the sensor irradiance to a brightness. So it was on the same axis as the exposure offset, but not optimized for each frame of your capture, but shared across all frames of each camera. And this was initially introduced when we have image metadata such as EXIF. So this would contain something like your exposure time, your aperture settings, your ISO, etc. Then it would really help because it can kind of bridge this translation as well. But that was before we tested with the controller module as well. And finally, when we went back in the end, across all sequences, the effect on the metrics that we tried to show improve for the paper, it was kind of a wash. And it was just adding complexity for no big benefit. And furthermore, with the controller module, we found that the controller, which is the kind of fifth module, it is able to explain or do this translation from the EXIF parameters to the apparent brightness in the image already on its own. So we just dropped it because it's just unnecessary complexity, basically.
So PPISP is working on different or with different models to like fix the differences between the cameras, basically. Is this something? I mean, when you build in the model modules, is this something you chose because it's like the selection is the one that solves the problem best so far, or is it something that is basically the easiest way to solve, or are there any things that could be included but are way harder to solve?
That's also a good question. So yeah, as I said, we try to be kind of practical about it in like choosing what we want to explain away and not to fall into the same traps that we were trying to solve on top of bilateral grids, which was overfitting to the different differences. And so for each of these modules, like the exposure, for example, this is shared across all the pixels in an image. This correction, I mean. So the model cannot make one pixel brighter and one pixel darker, for example. So it's really a consistent signal that needs to be there that the whole image should be brighter or darker. And so for an image, that's like tens of thousands to millions of points, of data samples points. And for the vignetting of, for example, which is shared across all the frames of a camera, you have like, I don't know, tens of millions of samples that need to be pushing in a consistent direction for it to learn that part. And that means that it's a lot easier to disentangle that from the scene reconstruction and also from each other, because they try to tackle independent tasks, so to speak. This was kind of part of the design philosophy we try to follow. You could also say that it's not trying to do corrections based on some data prior. So it's not a huge AI model that has learned like millions of images, nothing like that. So we don't try to like push things towards some nominal reference. We just try to reconstruct what's there and then figure out what are the differences between the input images, for example.
And I think some issues that if you don't correct for these differences, you are encountering or people are seeing are floaters, right? Because this is like, especially Gaussian splatting is trying to correct for these differences. And many people are very annoyed about this because if you look from one direction, you don't see them. It looks like perfect geometry. But then when you pan the camera a little bit, then you see, oh, there's like a big floater and you really don't know why it's there. But it's just there to do these corrections, right?
Yeah, exactly. So in the explanation video for this work that we put on the website as well, I took this photo data set where I also use exposure bracketing, which is this technique where you take a photo and then you apply a positive and a negative exposure correction. So you take 3 or 5 or 7 shots. And this really brings out the floaters if you don't compensate for them. Because what ends up happening is that the reconstruction will start putting these dark or light huge floaters near the camera to simulate the exposure correction within the geometry instead of having it in a separate model. Yes.
And what happens now if you have this PPISP correction? Is it now possible to go in the morning there, capture the object, then in during lunchtime, and then in the evening? Would it fix all the problems?
No, I wouldn't. So yeah, as I said, for example, if you have shadows in your image, like hard shadows, and PPISP not being able to change any of the image edges, it means it cannot deal with things like shifting shadows. So there's some other approaches. I mean, there was NeRF in the wild, for example, which started using these GLO or glow embeddings, which was basically some learned vector that could really modify the image quite freely or the image appearance. There was of course a follow-up applying similar techniques to splats as well. So for these morning to evening or like noon, different data acquisition that you try to bring together, PPISP is not the right tool. It's the right tool for dealing with like automatic camera differences or like exposure bracketing, things like that.
I think you can also apply it like it's representation independent, so it would also work with NeRFs, I guess.
Oh yeah, we did start developing it on NeRFs actually. So the bilateral grid was also published testing on SIP-NeRF, for example. And then for the paper, because it's just difficult to compare the results, we have included SIP-NeRF, but it's running mostly like a correction module on 3D Gaussian based methods. But it does work on anything basically. It's just a post-processing that you slot in the middle between your rendering and your loss evaluation. And for the controller, you will need to render out all your images, and then it can learn the correlation between parameters and input, or let's say training views. Of course, it will then try to generalize to the novel views as well. Yes.
And when we take a look at some of the, say like differing images in terms of exposure value or settings, one paper that you also mentioned was NeRF in the dark, otherwise known as, I believe, RawNeRF. And they started to really show that really high noise data was able to kind of be like abstracted away in a pretty clean way. Is this something that could also be beneficial through using PPISP?
In theory, yes, but with the noise, it gets really tricky. So from my experience, NeRFs are slightly stronger in the sense that they regularize towards a smoother representation, right? So with Gaussians, if you have your budget for Gaussians set high enough, they will be able to start reconstructing the noise that you have in your input shots. So PPISP, we chose not to include a noise model because usually it's not a huge deal. But I know that RawNeRF or NeRF in the dark, it also made an interesting and important point that if you have these methods, what you're basically doing is you're doing exposure fusion in a sense. So you're merging information from different exposures, and of course, if you expose for longer, your signal to noise ratio is going to be better. So that means you can reduce your noise in locations that are difficult to do with just single image captures, or even these more like static methods that operate on images. If you have like a 3D representation and your novel views are really good, you can use that for denoising. You can expect a slight effect for PPISP, but since we don't model noise, and because these Gaussian representations are better at actually modeling the noise you don't want to model, it may not have the same quality as this NeRF example did.
I guess a similar question to this is now, when you were first actually building this out, because you said you like started with like NeRF and now you're building this out. Was there a big moment where something that I guess worked better in NeRF or splats didn't translate as well? Like, did you ever get stuck at all at any point during the research process, or were there any like big learnings that kind of like started to facilitate more success for you and your team?
Yeah, I guess the issues weren't so much from the transfer from NeRF to splats. Actually, this transferred quite seamlessly, I would say. But I remember for example, for the camera response function, the CRF, which is this tone mapping module at the end, we went through a few different iterations. So first we tried the previously existing approach, which is you have a few nodes that you interpolate to form a smooth curve. And then you try to regularize it in a way. It should be smooth, it should be monotonically increasing. But that turned out to be actually not so stable. And when it fails really badly. And so we tried something else. And the next thing we tried there for the CRF was inspired by game engines. So in game engines, you usually have this, let's call it filmic tone mapping, where you have a few parameters that you can tune. So you can adjust the toe, which is the gradation of your dark values. So the shadows in your image are going to be controlled by that. And then your shoulder, which is the equivalent for the brighter values. And so you have a few knobs. So I already like this design because it's low dimensional in nature. It's just a few knobs. And this follows with the rest of the philosophy that it's a few different control points to really constrain your corrections. But it turned out that this filmic tone mapping was actually quite difficult to optimize as well, because it has these dependencies to always ensure that it is smoothly connected, etc. So finally, we came to this final iteration. And then one anecdote I want to add here as well for the color correction is I always like this color homography, but we also went through a few iterations there. And interestingly enough, I was like trying to optimize this a little bit with some AI agent, and then the AI agent claimed, oh, actually this simplifies to like a 3x3 matrix inversion or something like that. I was like, oh, well, I don't know. I don't see that. And it turned out to be true. So this final design that we have now is a lot more GPU friendly, because we used to do like a bigger inversion in a different way, and it's not as friendly, but now it's better.
Yeah, sometimes these models can help you, right, with some new
They can.
insights and so. We have been talking a lot about the different modules and maybe the controller, but we didn't say right now what the difference is between the modules and the controller. What does the controller do differently than the modules, and how does it relate to the modules?
Yeah, right. So in terms of the process in which it is used, the four modules, the exposure correction, the color correction, the vignetting, and the CRF, these are all capturing how the camera would do a certain thing statically. So if you had certain camera settings and your certain scene, this is how they would behave. And the controller, in contrast to that, it really tries to model the dynamics of the camera. So it's trying to model, based on the light that enters the sensor, how would it change its parameters for the capture. So the controller internally works by analyzing the image. We have a fairly lightweight neural network that then outputs directly the exposure and color correction. So it really controls the other parameters dynamically. That's how it works. And in the training, the way it works is we first do the training just overfitting all the parameters. So we learn all the four static parameters, so to speak. And then we freeze everything, and we just learn the controller. So the controller can learn the correlations between the input and the parameters that it can output to control for novel views.
So it's kind of, let's rephrase it. It's basically something like the modules learn the training images, right? They overfit a little bit, and the controller is like a virtual camera, which moves around and do some kind of interpolation to just interpolate between the cameras, the exposure, for instance, or something like, so that it looks more natural, like a real image, right?
Yeah, exactly. Of course, this is important for some applications. So if you have a situation like you have a robot and you want to do a sensor simulation, and you let the robot drive around freely in your Gaussian scene that you've reconstructed, then let's say there's some downstream model that runs on top of your images. Then it can be quite important that your simulated novel views, they look as close to the input in terms of their quality and brightness distribution as possible. So that's where the controller can actually help, right? So because it gets closer to what the camera would produce in that situation.
But then it's like not only important for robots, right? Because also important for humans, because if you look like a capture and you see all the difference and the controller tries to equalize for it, or just interpolate it away, which makes just a nicer appearing, right? If you look at it. But at the same moment, it's like an additional module, right? So if you are having the Gaussian splat, like the PLI, it's not included, right? So it's like an addition on top.
Yeah, that's a good point. So that's also an issue we're tracking, and I know Lichtfeld Studio, you also you have this PPISP sidecar file currently, which tries to account for these extra things, which are not in the ply file, right? And I mean, there's two sides to this. So if you train with PPISP and you export your ply or your USD set or something like that, then you already can get some of the benefits. Like it may improve your geometry by reducing the floaters or making the surfaces sharper, which is one part. And then the second part is yes, if you can model or export some of that as well to reconstruct the actual image look, then you can get another boost in the quality.
Mm-hmm. And without it, so I noticed that it looks a little bit darker often when you don't have the controller.
Yeah, this is, yes, we had this feedback a lot, also internally. And I think this is usually caused by the tone mapping, because the tone mapping changes the relative contrast of the brighter and the darker tones. And usually the linear color space looks a lot darker. And so it will reconstruct something closer to a linear color space. And then it's missing that uplift, which usually happens when you convert to sRGB. And I think you're trying to hint at this baking approach, which is also was under discussion before, right? And we have, so baking in that sense would refer to trying to transfer some of the appearances that you've learned to the actual model. So first you explain it away, and then you try to re-infuse it into the model somehow, right? That's the baking process. And I thought this was quite easy, but it's we tried the obvious approach, but it's not as trivial as I thought. So I underestimated it a bit. I think the baking itself could be an interesting follow-up work as well. Like, how do you bring that back into the model?
So we were talking a little bit earlier about both EXIF and metadata, and so I wanted to expand a little bit more because I feel like we don't often talk about the existing metadata in the input images that we use, and so I wanted to ask about like how it really practically affects or aids the PPISP, and then what people who are out capturing could be potentially doing differently to get better reconstructions using metadata.
Right. So I remember we did a small experiment to see what effect does PPISP, when added as a module, have to your reconstruction quality. And we found that, and we measured the amount of exposure variations as a kind of a proxy for how much photometric variation is there in general for that scene. And we found that if the exposure variations are larger, then PPISP will also benefit your reconstruction more, right? So when you start to have these data sets with very large variations, for example, HDR-NeRF. So here I'm referring to the data set, not the work itself, but they're connected. So the HDR-NeRF data set, they also use exposure bracketing. Actually, it's a super clean data set. And so without this correction module, you will run into some issues because the exposure varies a lot because they controlled it. They put like +2 EVs, which is 4 times more light, and -2 EVs, which is a quarter of the light. So the total dynamic range is like 16 times the linear light. And there, it really starts to help a lot. However, since these were manual overrides in the camera, so they set the camera, okay, now take a photo with +2 EV, now take a photo with -2 EV. The controller cannot recover these, right? Because it tries to find correlations between the input and the settings. But if you have a manual override, some human operator or some setting in the camera, then there's no correlation. So in that sense, or in that case, it needs to rely on this metadata, which we can also feed into the controller, that it can learn to predict, oh, actually, here we're using a darker exposure, so the image is gonna look a lot darker. And so then this is very important. And then you also asked for camera operators how they can benefit, right? So I think actually this kind of exposure bracketing is something I would like to do more often because, first of all, it allows you to recover HDR data, which is quite nice for certain applications, right? Because you're capturing a wider dynamic range. And for something like PPISP, this is also beneficial. Since you're doing these exposure captures, you're capturing more data for the different ranges of your whole dynamic range. So it's really constraining the whole optimization a lot better. So I would like to see this more often, actually. And of course with EXIF data. Otherwise, it's hard to kind of guess. I mean, you can recover it, but the controller will be confused if you don't supply this override data to it.
Does it also, I mean, PPISP have a positive impact on the geometry itself? And by that, I don't mean like just explaining away floaters, but if you think of meshing, for instance, would it help to improve the geometry itself to allow for better meshing?
I'm going to say yes. So we wanted to test this in detail, but we ran out of time. But we were really happy to find that there was a follow-up work actually that did test PPISP as part of their own method. And of course, their own method is a little bit better. But PPISP was also fairly competitive in that. And what they did is they actually measured the geometric quality, I think not in terms of floaters, but in terms of how close does it align with the ground truth mesh or point cloud? I'm not 100% sure. So they used the tanks and temples dataset, which has these really high quality scans. And they showed that the quality improved. So the closeness to the ground truth geometry improved, which I assume also translates to meshing, for example.
Mm-hmm. And compared with, like, say, a modern phone using, more computational photography, does that help lower or present larger challenges to account for compared to just like pure like raw images coming from, more traditional 2D cameras?
Yeah, that's actually a really important point, right? So our model is simple, and in modern phones, this goes back to what we talked about before. So there's some processing going on at the camera, and in modern phones, they do more processing. So there's a bigger black box between your incoming light and what it outputs. So there's a bigger unknown there. And they do all sorts of things, like they do this HDR fusion, so they capture like multiple frames and fuse them somehow, which is usually proprietary. So it's really a black box in terms of the method. It doesn't know how these images were captured. They do also, I think that's a big one as well, they do this local tone mapping where they try to flatten the image somehow so that your face, for example, stays nicely exposed, but also you have a darker background, which then gets lifted, and all of these kinds of effects, right? So this really makes the job harder for this kind of post-processing module to kind of explain it away.
I think you mentioned also in the paper that sometimes less powerful models might be even better, like PPISP in this case. And there's also like an example where you talk about combining PPISP with bilateral grid, where you just measure on the training images that it improves the visual fidelity, but then apart from that, it degenerates the visual fidelity of the reconstruction. How is that coming?
Yeah, that's an interesting effect, right? So we try to kind of estimate, are we underfitting or overfitting? Like, where are we in this regime? So let's make an extreme example. Let's take a really powerful model that can model any effect, or let's start with a 3D model. So you take your images and you try to figure out where they are in space. And so a consistent solution for the really powerful model would be to put like a tiny square of each, or like a tiny rectangle of each image in front of each camera. And that would be a perfectly consistent reconstruction in terms of the input, because yeah, every time I look at the training view, it's showing the image that I put there. But of course, this is very much useless for novel views because it completely doesn't generalize. And it actually behaves similarly for these image models. So for bilateral grids, I can say we had an early failure mode that was quite interesting. So we were using back then bilateral grids on NeRFs. And in one sequence that we had, the bilateral grids actually vacuumed out all the color information from the NeRF. So the NeRF itself became black and white. And bilateral grid was adding back the color in each view. And of course, when you then did a novel view where the bilateral grid does not generalize to, then your reconstruction was black and white, which is obviously overfitting to the training by being too powerful in that sense. Yeah.
Okay, that's interesting. Especially if you debug it, right? Because then everything looks black, and then you pan your camera or rotate it around, and then you see like color popping up. So what's that?
Yeah. It was pretty funny. And then like, it's possible to work around this, of course. So you do some learning rate warm up, and then you kind of heavily regularize it, and then this is not an issue. But this is something we encountered, which is a possibility with bilateral grids. Yeah.
And I'm curious too, now that you've like completed this work, some of the things you spoke about was like tone mapping, you talked about like noise too. Are there other like photometric components that you would like to continue to build out into either PPISP or in general?
You mean like version 2.0? I mean, yeah, there's a long list of things you can model, but Sean, who was the supervisor on the research side for this project, early on, I think he made a good call when he said, yeah, we want to limit the scope a little bit, because I also wanted to try more modules and trying to model more of these effects. But the tricky thing is, the more of these effects you try to model, then it becomes harder to disentangle that from your scene reconstruction. So it goes a little bit back to what we talked about before of overfitting as well. And as well, you want to disentangle them from each other. So as soon as they start competing for the same kind of task that the camera would do, it gets tricky. But that said, I am still interested in this kind of like modeling the local tone mapping, because this is so common in smartphones these days. And I imagine as well, like something like a drone, which has this more integrated camera. And I think it would actually still work fairly well, because it could either work together with the existing tone mapping that we have, which is global, it's not localized, or it could even replace the global tone mapping entirely. So that's something I would be curious about to see. Yeah.
So what was remarkable was like after you released the paper, how quickly it got adopted by like different methods. And I mean, up to this day, it's like everybody loves to use it. It's not very often that you see like a method published in a paper which gets such a fast adoption and also like kind of proves the test of the time. I mean, it's not too old, right? But it seems that it already became industry standard to a large extent. So was it surprising for you that it would be so successful? And on the other hand, I mean, if you know that the method is like very powerful in itself, it's kind of very generous to give it away, because otherwise, I mean, it wouldn't be there, right?
I mean, yeah, thank you so much. And also like right back at you, because I remember Lichtfeld Studio had it really early, right? So you implemented it within a couple of days, you had something running. I remember also Florian, another researcher, had it quickly running. And to be honest, I was completely blown away, right? We kind of wanted to release everything in one day, so have it ready also in gsplat and in 3D Grat, which are two other repositories. And what we wanted to have also like a clean library that people could start using quickly in some way. But we didn't expect it to be so popular quickly. And I was really happy to see like the reactions and, oh, people are using it, it's actually working. And yeah, it still makes me happy to this day, for sure.
I actually have a question for both Janusz and Isaac on this one. And as like a developer then, and like taking that library, because PPISP is, open source and it is Apache 2 license, meaning you can use it commercially. Janusz, how was it actually taking the library and then putting it into your actual repository and workflow?
Well, I mean, it was pretty easy because everything was written in CUDA kernels, and Lichtfeld is using CUDA. So it was copy and paste with a little bit work around it. So it was like a matter of a couple of hours to implement it, fairly easy. And people could starting to try it. And yeah, so thanks for this and make it so easy and fast. I mean, I usually try to implement methods from papers which come without code, and then I sometimes succeed, sometimes not. And there's always a question, okay, am I doing something wrong? So mess that somewhere up or not? But this, if you have like a very nice license model and you can just more or less copy it over, it's very convenient. And I mean, that's something that proves that it works and people use it.
Yeah. And in that same way, since it's like pretty easy to stand up and get up and running, do you think, Isaac, that we might see it make its way into more of the NVIDIA ecosystem in places like either Isaac Sim or into NuRec as the general library?
Oh yeah, for sure. So yeah, it's already in NuRec. We're just updating it now. And in Isaac Sim, this comes back to this earlier question a little bit, where we tried, there's this extra step that you can have in the implementation where you try to also have this dynamic aspect. So what we're now doing is we're tracking this issue and working on how we can export PPISP as a shader. So it was really also designed to be similar to a kind of pixel or fragment shader, as well as having this controller as a lightweight neural network. So the idea is that we can export this as a Slang shader and embed it in the USD set, and then load it back in Isaac Sim. And then Isaac Sim will have the reconstruction, which is using this new particle field schema in USD, and then can also run the shader on top if he wants to do things like sensor simulation. Yes.
And expanding on top of that, then, so once it's in Isaac Sim, how can PPISP then benefit physical AI?
Yeah, I think that's a really positive question as well. So I think most importantly, it helps with these setups where we have multiple cameras. That was also one of the initial motivations, where we had a car scene with like a fisheye camera that had really low dynamic range because it's a tiny sensor. And so it will blow out the sky almost completely. And then you have a bigger frontal facing camera. And so it can really bring in alignment these different cameras, which is another important aspect. So in physical AI, you often have a robot or a car that has multiple cameras. So it can help with that. And then another way, which we talked about already, is hopefully it can help with the geometry a little bit. And of course, also, that's also something we also talked about already, which is the kind of sensor simulation you can do. So you can say, okay, render me this view, but also simulate this fisheye camera or simulate this larger camera, right?
I mean, one additional question I have, I think we touched a little bit on it, is just on the dynamic side. So similar to something like 4DGS, if this is something that can slot into that world as well, or is it really primarily geared towards static capture?
Oh yeah, that's a good point. Yeah, we do already have something similar in NuRec, right? Which means that when you animate, for example, when your car moves through the scene and there's other cars moving and other objects moving, and for example, your car exits out from under a bridge, so the exposure is going to change dramatically, like actually going down. So we do already have some tweaks to make it work better in that scenario. So one thing you can do is you can just apply a temporal smoothing over all your per frame parameters. So you can say your exposure shouldn't change that much. So you can smooth over the exposure and the color correction. And this is quite a trivial addition to the regularization you can do on the existing model. And I think then it can basically work for that kind of scenario. One thing that I find is a bit tricky here, I guess this is kind of extending on your question a bit, but I just remember that for things like generative AI, which is also now producing Gaussian splats, of course, the question of color spaces comes up, right? So when you produce something generatively, then the question becomes, how does this relate to this other scene or this other like even image that you may generate also? Does it also have like an exposure offset? Does the generative model understand the exposure offsets between images, or is it something else? So the question again becomes, is there a black box that we can model, or is it out of the distribution that we can model, basically?
Yeah, that's fascinating. And yeah, we really want to thank you for coming on to the View Dependent podcast today and, spending some time to talk to us about PPISP. Like Giannis was saying, it just has been integrated so quickly across so much of this ecosystem. And, I'm always more and more excited to see how we can recover more information about the physical world and display it in a really lifelike capacity. So thank you for coming on.
Yeah, it was a lot of fun talking with everybody. And yeah, thank you so much again. Yes.
And thank you very much for your insight. I mean, it's always interesting to read a paper, but getting some background information about it, what was the reasoning to create the paper or do the research in the first place, is always very interesting and also gives maybe a slightly different perspective than just reading the paper. So thank you very much for spending the time with us. Thank you.
Thank you.
And we will return soon with future updates and episodes looking more into the world of super lifelike 3D. But until then, thank you so much, everyone, for listening or watching today.